Welcome back, everybody. Today we're going to keep playing around with parametric equations and really dig into the two calculus type formulas that we were introduced to last time. And a quick recap of the story so far is that we have a particle zipping about. Right? We got a particle, and as time moves forward, that particle is moving around the plane, tracing out some path. And we can describe the path that our particle takes with two functions, right? One that shows us the x-coordinate at each point in time, and another function that shows us our y-coordinate at each point in time. And we saw two formulas last time. One handed us the slope of the tangent line to our curve at a particular time t. This is the formula we saw. And again, the idea here is that, let's say if we're at a particular point, like this point right here at time t, well, then we can sketch in the tangent line. That makes sense to talk about. Right, and the slope of this line, that's what we're calling the dy dx, and that's what our formula hands us. Over here on the right, we have our arc length formula. And so the idea here is, well, if we start at time A and let our parameter move about and then stop the movie at time B, then we trace out this kind of string, it looks like, and the arc length formula wants to take that string and just lay it out flat and ask, hey, what's the length of this curve? And that's exactly what our arc length formula hands us. So we have a worksheet today to play around with these ideas. I just have a couple of notes before we start in with that. The first note is thinking about, I guess, how our formulas work. Specifically, if we think about our parametric equations, the way that they work is they take a particular time t, and once we plug in t, these are going to spit us out x and a y coordinate. Right, and our slope of the tangent line formula, it also takes in t values and then spits us out, the slope of the tangent line at that time t. And so sometimes, depending on what question we're asked, we need to do a little bit of translating in order to answer it. So an example of something like this would be, well, let's say we have our curve, and we actually want to know, hey, what is the slope at this particular xy point? Maybe it's like 2, 3, or something like that. Well, if we think about our slope of the tangent line formula, we can't hand it an xy point, we can hand it a t. All right, and so if what we know about is an xy point, well, then we first need to translate that into a t value. We would need to take this point and figure out, hey, what t value corresponds to this point? What t value gives us this point through our parametric equations? And once we have that, then we can plug that t value into our slope formula and get what we want. And so sometimes we need to do a little bit of translating one way or the other, depending on what kind of question that we're asked. The second note I wanted to make is that if we want to compute arc length for a particular curve, we need two things in order to set up our formula here. I'll just bring that up just for a second. The two things that we need, the two ingredients, that takes are, first of all, our parametric equations. We need to know those. And we also need to know our starting and stopping t-values that start us where we want to start, stop us where we want to stop, so that we exactly trace out the curve that we're wanting to find the length of. All right, so that's it for my little introduction here. If you haven't had a chance to work through the worksheet yet, pause the video here and see how far you can get working through that. Afterwards, we'll talk through each of those questions. All right, well, let's start talking through the worksheet. So here we have a parametric curve in the plane, and our parametric equations parameterize this, and they hold for all t. So t from minus infinity to infinity. And the first part here is asking us to figure out essentially how we're moving through this curve, how our particle is moving. Right, and so here, if we take each of our parametric equations for x and y and graph those with respect to t, well, x is just a parabola pushed down by 1. And so here, I guess that'd be -1. And to graph y, we can actually do that, but it may help to factor this if we want to do it by hand. We pull out a t and then use difference of squares here. See that this is a cubic polynomial that has roots at 0, +1, and -1. And since the leading coefficient is positive, it has the standard kind of cubic shape and cuts through our t-axis at -1, 0, and 1. And so looking at these, kind of feeling out what's going on with our x and y coordinate of our particle, I think the cleanest way to see how we're moving here is by looking at our y graph. Right? When t is negative, our y coordinate is negative as well. And then as we increase time and move to the right, y is doing something, but eventually it's going to be moving up to positive y's. And so if we look at our curve over here, well, the only way that we can get our y coordinate, more and more negative is by trailing down this tail here on the bottom right. And so as t increases, we're going to be moving up this tail to increase our y coordinate, right? Then we get to some sort of local maximum for our y coordinate, then start coming back down, and then get higher and higher and higher again. And so here from this picture, we can see that we're tracing out our curve this way. If we look at our x coordinate graph, all it tells us is for negative t's, x is positive, and then it's negative, and then it's positive as t increases. And so it's not clear whether we're moving kind of down or up from that graph. And so really the y coordinate graph allows us to see what we're up to and how we're moving. All right, next we want to find our formula for the slope of the tangent line. And so just using our formula as a recipe, we just put the different pieces where they go, just those two derivatives, and there it is. We could simplify it if we really wanted to, but there's no need. We can just leave it like that. So this is what would hand us the slope of our tangent line. Whenever we plug in a certain t, it would hand us the slope of the tangent line at the point corresponding to that t. Well, let's bring down the rest of the way. All right, so part C here, we're wanting to find the slope of each tangent line to the curve at the point 0, 0. And so here, maybe the phrasing here is a little bit odd. Notice we actually go through the point 0, 0 twice, right? Once at the start and then once again after we move through this loop. And so we actually will have, two different tangent lines. Those are supposed to be lines. Right, but in order to do this, right, because our slope of the tangent line formula needs t's to plug in, we need to figure out, well, what t value gives us the origin. Once we know that, we'll be able to plug that in and grab our slopes. And so, well, if we want x and y to both be 0, well, then we want our x coordinate function and our y coordinate function to both be 0 for the same t. And so we have these two equations we want to solve. And so working through the first one, we get plus or minus 1. We'll make our x coordinate 0. And again, factoring our y function, we can read off that the solutions there are 0, 1, and minus 1. And again, we're looking for the t's that make both our x and y coordinate 0. And so we're looking for the t's that are in common to both these solution sets. And the ones in common are just the plus and minus 1. Right, if we wanted to see, if we were wondering, hey, well, what about this t equals 0? Well, what happens at t equals 0? Our xy point is going to be 0, minus 1. And then the y coordinate would be 0, minus 0, so 0, right? And so that's not the origin. All right, so only plus and minus 1 will give us 0, 0 as our point. And so now that we have our two t's, we just need to one at a time plug them into our dy dx formula and see what they tell us. And in this case, it looks like at t equals 1, our slope is 1, and at t equals minus 1, our slope is minus 1. And so maybe just as a quick sanity check, let's see what's going on there. Right, so we've seen that we first hit this point, the origin, at minus 1 for t, and indeed the slope of the tangent line looks like about negative 1. And as t increases, we hit this point again at t equals 1. And again, looking at the tangent line there, a slope of 1 seems reasonable. So that's nice. All right, next, we're looking for the xy points where our curve has a horizontal tangent line. And just thinking about slopes of tangent lines, for this tangent line to be horizontal, then the slope of the tangent line needs to be 0. All right, and we can kind of scope these out on the graph up here. All right, these are going to be right over here. We got a horizontal tangent line, and over here, underneath it, we have another horizontal tangent line. And it looks to be like that's going to be the only places where that happens. And so we kind of know what to expect for our solution. Well, let's go through and algebraically find these. Here again, we need to do some translating. Right, if we want to know these points, well, our dy dx formula involves t. And so this won't give us what we want right away. We'll need to do a little bit of translating after solving our equation that we get. All right, so here, just multiplying both sides by 2t to clear out denominators. 0 times 2t is just 0. And so solving this equation, we get t is plus or minus root 1/3. All right, and so these are the points in time when our tangent line is horizontal, but we want the actual points. All right, and so in order to get our points, once we have our points in time, we need to actually plug in to our parametric equations, and those will hand us the x and y. And so if we just go through and do that, plug in our two solutions here, positive root 1/3 and negative root 1/3, we get these hideous looking points. If you plug these into your calculator, you can get a little decimal approximation here. And from what I remember, I think that our two y coordinates, I can't remember which one goes to which, they're about like 0.4-ish or something like that, 0.38 or 0.39 or something. I guess plus or minus that. And so now, with these two xy points in hand, let's go back to our picture and just see if that checks out and looks reasonable. So the x is negative 2/3. So a little bit past negative 1/2. Yep, that looks good. And then about plus or minus 0.4-ish. That looks pretty reasonable as well. And so we're feeling pretty good that we did our work correctly. All right, next, part E, looking for the points where our curve has a vertical tangent line. And so thinking about our formula for the slope of the tangent line for dy dx, which is, y prime of t and x prime of t, if this is going to essentially give us infinity is the idea, well then we would need to have our denominator equal to 0 and just our numerator something else. And so that gives us an equation to think about. So x prime of t, derivative of our x coordinate of our parametric equations, gives us 2t. And so this is happening when t equals 0. And I guess if we wanted to, we could check out y prime as well at t equals 0, right? Y prime would be 3t squared minus 1. And so y prime of 0 is minus 1, which is not 0. And so indeed, this will give us a vertical tangent line at t equals 0. To get our xy point, we just need to take our time and plug it into our parametric equations. Right? And this is the point that we've done before. Minus 1, 0 is what we get. And indeed, quick sanity check. Minus 1, 0 is right here on the left. And indeed, tangent line there is vertical. Okay, so that's it for playing around with this parametric curve. The second one in this worksheet is thinking about arc length. And so here we were asked to compute the arc length, or use the arc length formula to compute the circumference of a circle of radius 4. Right? So something like this. And so, as we mentioned before, if we're going to use our arc length formula, well, we need our parametric equations for our curve, and we need our starting and stopping times for our parameterization. Now, if you recall, one of our first examples, we had this kind of ellipse, and it went out 4 as its kind of horizontal axis, and as its vertical axis, it went up 2, and we used 4 cosine t and 2, that's a typo, sine t. To parameterize that. Well, in general, the a and b on the cosine and sine here are going to tell you these axes of your ellipse. And so here, if we want a circle, well, both those axes are the same, and so we can use 4 cosine t and 4 sine t, and then to start at the right and just move around this circle exactly once. We'll use 0 to 2 pi for our parameter values. And so just taking that and feeding all that in to our arc length formula, we just have a couple of derivatives to compute. Negative 4 sine t for x prime, 4 cosine t for y prime. And once we've done that, we just have some algebra to do to work through this. And what's nice about the circle situation is that now, once we take this square and distribute it to the negative 4 and sine and the 4 and the cosine, we get a common factor of 16 that we can then pull out. All right, so it's still inside the square root. To start, we get 16 sine squared t plus cosine squared t. And hey, this is something that we've seen before. Right, our sine squared plus cosine squared, that's a nice clean 1. And so this boils down to root 16 times 1. So just root 16, which gives us a nice clean 4 to integrate. That's just a constant, and so to integrate that, we just multiply by our variable, evaluate from 0 to 2 pi, and so we'll get technically 4 times 2 pi minus 4 times 0, which is 8 pi. And this is also an example where we can kind of do a little sanity check. Right? We've known since forever what's the circumference of a circle? 2 pi r. And in this case, our r is 4. And so 2 pi r is exactly 8 pi. And we can even see that real clearly just with one step before. Here's our 2 pi, and here's our r. So here we've actually used calculus to I guess, discover and verify this geometric formula that we just know from forever back. All right, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.